Okay, shall we start? Hello, shall we start?
Yes, sir. Yes.
Okay. See, today what I'm going to do is spherical basic. Spherical harmony and spherical basic.
You had said in the previous class about the date for the exam
Yeah.
that will be fixed.
Hello. What date do you prefer for the exam? Are you here? Are you able to hear me?
5th January? Yes, sir.
Uh, 5th January? Is it okay? Hello.
Yes, sir.
So date 5th January, what 2 to 5? What day is 5th January? What's the day?
Side, so Wednesday.
Zero. So this is the date for the exam.
But the syllabus will be from after the midterm, right?
Only post. Is it visible? Okay. So this course. Okay. So now this is spherical. So the spherical, the right hand, is then it is and I project.
Hello, sir. Sir, your voice is not audible clearly.
Is it better now?
Yes, sir. Now it's better.
Okay. So I will do this projection. I'm going to do it onto the XY plane. The projected vector is projection will have an angle P with the x-axis. So this will be the x component and this will be the y component. And what I have, that is equal to r, x is equal to. So let me start. I have x is equal to r sin theta cos t, y is equal to r, and z is equal to r cos. So this defines the xyz coordinate in the relates polar coordinates to xyz coordinate. Now the thing that I want to do is the Laplace operator, which in terms of r theta. Okay, to do this, what you have to do is first know what del squared is equal to del squared by del plus del squared by del plus del squared by. This is a very important operator because the kinetic energy the Hamiltonian is given by minus h cross by 2m del squared, and it has got eigenfunctions and eigenvalues p of k equal to h cross squared k squared to 3m. Okay, so indeed the ik dot r is del squared by del squared by del squared, and I can take psi xyz as equal to some function x of x, y of y, z of z, the product of these. And when I do this, I see that this is coding is equal to psi will break down into the following minus h dot del squared by x of x is equal to say ex of x of x, and so x of x would be nothing but e to the I kx times x, and ex is equal to minus h cross squared kx plus by 2m. Okay, and similarly I'll get phi of and that. So my total waveform kx x e to the I ky y e to the I kz z, and my total energy is going to be ex plus ey plus ez is equal to h cross squared by 2m times kx squared plus ky squared plus kz squared. So this is the standard free particle calculation, and what we want to do now is in r theta p coordinate. So to do this, what we have to do is get the function r is a function rather than. So what I do is so del x del r by into del by del r plus del theta by del x into del by del theta plus del phi by del x into del by del phi. So this is how del phi by del x will be, and you can get similarly del f by del y and del f by del. So this will give you the operator del. Okay. So in order to get that, okay. So what I have the following: z is equal to r. So if I want to know what is r, r is equal to this thing, z is equal to r. That divided by r. Okay. And what I have is I have to now get the function del r by del x. Okay, so if I want to get this function del r by del x, then I must express that as the so I have r is equal to, so let me look at it this way: r is equal to root of x squared plus y squared plus z squared. Okay, so let me not so let me want to get del r by del x. Okay? Taking one. Okay, so if I want to get del r by del x, then what is this equal to? This is equal to this one, so del r by del x will be given by 2x divided by 2 times square root of x squared plus y squared plus z squared. Okay, and what is that square root of x squared plus z squared? So 2 and 2 goes. X is actually given by r sine theta cos phi, and root of x squared plus y squared plus z squared is equal to r. So del r by del x I know is equal to r theta cos phi. So this one expression I have. Similarly, I can get for this theta. So what is theta equal to? Theta is equal to cos inverse of z by r. Okay, because I had z is equal to r cos theta. So z by r is equal to cos theta. So cos inverse z by r is equal to this thing theta. So now if I want to get del theta by del x, then that's equal to del by del x cos inverse of z by r, or that's equal to 1 upon z divided by, let me go step by step. So that's equal to this thing. Whenever I try to differentiate cos inverse z by r, then that is going to give me 1 upon minus 1 upon root of 1 minus of z squared by r squared, because this, and then I have del by del x of z by r. Okay, so because this is the cos inverse t, so del by del t cos inverse t is 1 up minus 1. So what I would is actually minus divided by minus z, and del by del x cos inverse del by del x z by r is equal to z into del by del x of 1 upon root of x squared plus y squared plus z squared. So this will give me minus 1 divided by square root of r squared minus z squared times z times 2x divided by x squared plus y squared plus z squared to the power 3 by 2. Okay, and then I have a minus sign coming because when I differentiate root of x squared 1 upon root of x squared plus y squared plus z squared, I get minus sign divided by minus half times 2 times x squared plus y squared plus z squared is equal to 3 by 2. Okay. And z, okay, and on the top we start, okay, and then I have just 2 into r sine theta cos phi divided by 2 times x squared plus y squared plus z squared to the power 3 by 2 is r cube. Okay, so what we is minus upon r times, because r squared into input and that, and I have on top I have r squared and this minus 2 and minus plus 1, 2 and 2 cancel. Okay, and then I have sine theta cos phi divided by r cubed. Okay, so this should give me sorry, this book okay, so this will give me actually is r in the denominator, r cubed above. So I have somehow missed it. I have got an extra r somewhere, but just check it out afterwards. So what I'll get is this will be sine squared theta. So this is 1 by r. So I have a that here. So this is going to be r plus. Okay, so you'll have to you just do the. This is not sine theta, sine theta, and I have a r here, and on top I have a rho, and this one is minus 2x, so that's r divided by r cubed. So I have an extra r. Del, del x. So r sine sine. So 5 is equal to cos r p is equal to tan inverse y by x. Okay, so p dp by dx, if I want to get, then that is into 1 upon 1 plus y squared by x squared times so dp by dx is times minus 1 by x squared. Right? Because I have a tan inverse y by x and dp by d for tan inverse, if I differentiate, I get 1 upon 1 plus y squared by x squared. And when I differentiate y by x, then I get minus y by x squared. Okay, so if I keep this minus y divided by x squared plus y squared divided by x squared into minus 1 by x squared. So that is going to give me minus y will become plus y divided by x squared plus y squared. So that will be equal to y divided by r squared minus z squared, or that's equal to what is y? Y is equal to r y is equal to r sin theta sin p divided by r squared minus r squared into sin squared theta. So this is going to give me 1 by r sin p by sin theta. So this is going to give me p. Okay, so I have dr by dx, d theta by dx, and I also so if I have all the three, then similarly I can forgot it. So from this I del p by del x is equal to r plus dr by into del by del theta plus dp by dx into del by del t. So you can substitute for from what I have done here and you get f by t. So once you get df by del f by and del f. So once you get these, then what you need to do is go to the next. So to get the what so I have if I substitute for I have sin theta del f by del r plus 1 by r by del theta minus 1 by r sin p by sin theta into del f by del. Okay, so now if I want to get then I say then I want by is del square of okay. So del g by del that's equal to sin theta cos p del g by del r plus 1 by r cos theta cos p into del g by del theta plus minus 1 by r sin p by sin theta into del g by del phi. Now what you have to do is you have to substitute for del T. So T is del F by del X. So you have to substitute this in here. Then you will get the whole differential. So what you will say is so so we have just put and so you will get it's a pretty tedious calculation. You get to Laplacian is del squared equal to 1 by r del by del r squared del by del r plus 1 by r squared sine theta del by del theta sine theta del by del theta plus 1 by r squared sine squared theta del squared by del phi squared. Now, the solution for or theta p equal to some k psi r. Okay, so then what I need to do is I'll have to separate the difference for x y z as r of theta of theta, p of p, and substitute into this equation. So if I substitute, then what I'll get theta of theta, p of p into 1 by r del by del r squared times r of r plus this one is a function of just theta, so I'll pull out the r and the p of r. So I'll have r of r, p of p into 1 by r squared sine theta del by del theta sine theta del by del theta times theta of theta plus 1 by r squared sine squared theta into r of r theta of theta into del square by del p square of p of p. Okay, so this is equal to k times r of r theta of theta p of p. Okay, so following that is look at what we have p uh, yeah. Okay, so if I can define constant, then I will be able to pull out r of r theta of p of p, because this whole thing can be replaced with p, so we will become constant, and this part will become an eigenstate. Okay, so in order to do that, what I have is p of p will have the form p to the im phi. So if I did that, p squared a can be squared. So if it is p of 1 by r del by del by plus r of p of times 1 by r squared sine theta, or del by del theta, sine theta, del by del theta, minus m squared times theta of theta. Okay, so that should be equal to k of r of r, theta of theta, p of theta. Okay, now lambda by put it out. So I will get so what is that? Then so that's for this part, get the R equation. R equal del by del plus m squared by r. Okay. So this and theta of theta, rather r this multiplied by r of r should be equal to say some k times k times r. Okay, so this is what we really have to solve. So this is a radial equation. So let us first so to solve that. So what we have 1 by r. Oh, sorry. Yeah, we will have then theta is equal to. Okay, I'll show you that. So I have taken lambda also. Okay, so if I cancel out the r squared 2, then this is the equation and this equation. Okay, so I can make the rate. Say, let's cast. Okay, so Please remember that this x is nothing but Cartesian coordinate x, because the Cartesian coordinate is completely different x, just as it is. Okay? So don't confuse it. So if I then d by dx 1 minus and d by dx plus minus square this times y of x. Okay, so theta of theta will now become y of x because that's the variable. Okay, now so this is the point here. The Legendre definition. We had something d by only this part was. Now let us put this. Then now y of x equal to 1 minus to the power m is power. Okay, so if I say into this which is not uh, you, you don't this square minus this m plus du by d plus m and u is equal. Okay, so in what way is this different from the usual differential equation Legendre type? The simple Legendre differential you have minus x, and this you did not have lambda in the conventional or the ordinary Legendre. So this is different from Legendre. How it is? Okay. U of x using the Frobenius. That is the east. Okay. N equal to 0, a n x to the power s plus n. Okay, s is the inter. Then will be n into m plus twice m plus into m substituting stuff plus m into m plus 1 is equal to 0. Or I get is equal to m plus into m plus. Or I can always because I can write lambda. where L is an integer. Okay, and one thing that if the series for u of x does not run, then u of x tends to infinity at x equal to plus 1. Okay, the reason why this tends to plus minus 1 is important because x is quantity. So this has to be. So you want this function to be well behaved over the entire interval. So if it should be well behaved, then it's not good. So if it's not, then what is this? It implies that the series to terminate, yielding a polynomial, because whenever series polynomial. So it should yield, and when this is true when L is greater than or equal to M. So only when L is greater than or equal to M, it is going to be giving us a meaningful. And now you almost see that L into L plus 1 is like the total angular momentum, and M is like the Z component of the total angle. Okay, so in that sense, the Z component total angle. So that's the is Q and Q is this is called this by Q by K. If you substitute one, this one, and the reason why. So L is an integer and M has to be less than or equal to the integer L. Now, so let PL PL plus L in PL. If it is the output with respect. So whatever DM 1 2x L plus L into DM for N PL, This will again be equal to 0. So involves using the. So if you use the then what you is the 1 month into D dm by dx. Okay, so you see that when I pull it through without taking out the one minus. And the other, you know, you can control it and 10 is. So if you do that, then d by dx, dm by dl plus L into L plus 1 minus M into M plus 1 dm by dx. dl equal to. So what you will see is that if I were to differentiate the Legendre differential m time, then the equation that I'll get is the same as the equation for u. So u is actually equal to dm by dx to power m here. Therefore, we have dl. So if that is the solution y of x to the power m by 2 u of x. So the solution they will become 1 minus x times dm dx dl. So this the differentiation we get by u 1 minus dm by dl. Okay, so now you see that how I got the solution for this equation. So the way I got the solution for this equation was simply by substituting for y of x as 1 to the power m by 2 times u of x, and then get the difference lambda given by L plus 1, and this L has to be greater than or equal to m. I also find that condition is equal because you want to have u of x being finite at the intervals minus 1 and 1. That is possible only if the series that u of x should become a polynomial. So u of x is a polynomial. By actually showing that the Legendre differential equation is m times, then I'll get, and so u is dm by dx to the m plx, and since y is equal to 1 minus x squared to the power m by 2 u, I have y is equal to 1 minus x squared to the power m by 2 dm by dx to the power m plx. So this okay, so is okay. So PL minus M of is equal to 1 minus x squared to the power minus m d d L minus m by dx to the power L minus m dlx. Okay, so that is what we mean by. So they are L minus m. So now we have two solutions. That is theta of theta is equal to P L cos theta and P of P is equal to E for IM. Okay, so the into P of P is usually y theta P. Okay, or also written as y lm theta P. Okay, and this is equal to P lm cos theta into e to the power I m. Okay, now this is for m greater than 0, but for m less than 0, negative values. What you want to do is theta the following: they take PL minus m is equal to minus 1 PL plus m cosine. Okay, so in this case, you have a constant which is minus 1 to the power m that relates PL minus m and PL plus m greater than 0. And this particular tie is called this tie of the constant is called condensate. In fact, there are many different choices of phase for which are quite confusing. So one has to work consistently with the same choice of phase, and that choice of phase comes because of the way you find the relationship between PL minus modulus m and PL plus modulus m. If you take PL minus modulus m equal to minus 1 or m PL plus modulus m cosine theta, then is modulus. Okay, then you have Cotton shortly choice of phase, and this is what is most widely used. Okay. Spherical. So if you remember on a circle, the basis were constant, which constant, and and all over could be in so what was this called? This is something that we spent, and this is the Fourier. So when you go to that is, we are looking at periodic function. Here are in the case y, which are the so in a way generalization of the Fourier series to the sphere. So you can, okay, now what yeah, y star m prime theta p 0 to range p. So this will always be delta m. Okay, and you must remember p l m cos theta p l prime cos theta. You can have p l prime. So sin is only equal to, okay, you don't have a delta mm prime coming here because m and minus m are always related by a constant phase factor. So I cannot say that PLM and PL minus m are orthogonal. PLM and PL minus m are proportional. So I basically have so that's only delta LL prime. So the orthogonal different with the same L but different M comes about because of the phi part. Okay? Because you see that phi prime is okay. So this is the P of P D. So the orthogonality corresponding to different M's comes from these. And in fact, the solution of hydrogenic problem. Okay. I have done quite a bit of spherical harmonics. Go into more details because it's it's going covered in the bottom. And also, I think spherical harmonics and other products. So this was okay. So carefully. So, do the d by minus L minus K and equal to 0. Okay. So K squared was nothing but some constant minus, you know, equation. So now let us so uh, plus 2 of so I have to K squared of K minus times R of. So you see that before differentiating so that's why. And K squared becomes K squared R squared. This R squared of 2R d by dr plus K squared R squared minus L into L R of. Okay. So this is very similar. So now what I will take R so what I'll do is say that I change the value to root of. Okay. So if I get the following d squared. So this is the function of R and this of this. Yeah, so I'm changing the function. R of R is what I'm doing. So I do this d squared by dr plus 1 by du by dr 1 minus L plus half squared by R squared times is equal to 0. Okay. So what is it that we had for the this thing, the differential, the vessel difference. We worked it out last time. So the vessel difference equation that you have. So the vessels difference that we had was x squared dy d squared y by dx squared. Let me just go in here. So I had x squared y double prime plus xy prime plus d squared y is equal to 0. Now what happened is do is the following. So I could actually then I get d squared dy plus r du by dr plus r squared minus L plus half squared times u is equal to 0. Okay, now you see the following, that this is nothing but vessel differential for nu equal to L plus half. Okay, because the vessel differential equation for nothing but y double prime plus x y prime plus x squared minus y over the vessel. Okay, so here is the x squared minus u squared. You have u is equal to L plus half. So it's always a half integral, okay? Because L is always integral. And once we have this, so that u has solution that corresponding to nu equal to L plus half. Okay, corresponding to basically u is nu squared. If I say, then u is equal to L plus half and u is equal to minus L. And these are linearly being half integral. Okay, so usually for integer n, j and minus j minus n were taken because j minus n was so. But on the other hand, so j and j minus n, but when the index of the Bessel function nu nu is actually not an integer, then the Bessel function is linearly independent from plus. And so solution R of R, they having a form u of R root of R. So this is going to be j L plus half by root of R and R of R equal to into it. So this is minus of j minus L minus R divided by root of. I don't know, this is a question mark. And this is called a spherical Bessel function. And this one is called spherical Neumann function. Which is NL of R. Okay. So let me see if I can move it. And incidentally, I did slightly different things. So I should have had U of R divided by root of KR. Okay. So I first change the variable from R to K of R, and then R of K of R to U of K of R by root K. Okay. So I should have been a bit more careful because I have to have K of R. Because K squared, K squared R. Change the variable K of K times. Okay. So usually this is JL K of R and NL K of R. So we have the two solutions. Or the spherical basis. Spherical Neumann. So with this, what we have learned is the following. We have learned the solution is the solution. But this JL, KR, YL, theta Q is the solution. So what happens if you want? So e to the power I can be in terms of Bessel's function and spherical harmony. That is e to the IK dot L sigma or A. Okay, something like JL, K of R, Y, beta P times P LM. Okay, so CLM is the correct index. Okay, and this expansion is quite standard. You can look up any book on quantum mechanics, you will find it. Okay, and this is extremely useful. Let me move it up. This expansion is useful in problems involving scattering of free electrons by a cycle. So when you are actually having a spherical potential, the and you have the free electrons going through and getting scattered, then the angular part of the wave function does not. Because that continues to be the solution. And so you can look at this partial wave analysis is what you can do. That means you take each one of these waves and then see what happens when they scatter off the angular of the spherical potential. The spherical potential does not change the L or the M of the state, but only changes JLKFR. And at large distances, so JLKFR gets phase shifted. Because you know that JNCASR, for example, for J0 AFR is nothing but sine KFR by KFR, right? So this goes to a phase shifted thing, which is sine KFR minus delta by KFR. Or in general, any one of the always by some delta. So it's very, very helpful. Go to the coordinate, particularly spherical cube. Okay, so this is what no. For example, PR the case of PR, you have y10, y1 minus. Okay, so these are the solutions. Okay. You can actually learn about because angular momentum, critical state, and what you have, if you want to see sort you because L is a for all three states, we can form linear combinations and also PR. The hydrogen case, hydrogen or atomic case, p orbitals are degenerate. You can form linear combinations, and if you form a linear, what you px is equal to 1 upon 2 y bar 1 minus 1 upon 2 y bar 1. Okay, so this is x because y1 is actually cosine theta times e to the I phi. Okay, because p1 0 okay is equal to cosine theta, and this is e I phi, and y1 minus 1 is equal to cosine theta times e to the minus I phi. And y10 is just cosine theta. Okay. So if I take px 2I, this will give cosine times no, sorry, this is differentiated. Because it is going to be okay. So y10 is because I take p1 differential the function 1. Okay. So this is sin theta py is equal to 1 by this is y. Yeah, I'll tell you. So p plus y1 minus sin theta cos p and p1 0 pz is equal to p1 0 is equal to cos theta. So you see that what cos sin x sin. So if you forget photon, which is a constant, so if you have that this is given by the similarly this linear triangular right and z will be like the z. So these are called cubic components. Similarly, you can see that will have that is equal to if I take out unit here, then you see that z square is constant and x square square into cos squared p minus sin p. Okay, so because sin squared theta cos squared p is x squared and sin squared theta sin squared squared, and if you want to, you should go sin theta cos p into sin theta sin phi. Okay, so you will basically have to the angular part that you are looking at, that's the trigonometric part. Trigonometric product of coordinate. So you can write it out for any orbital. So supposing if I tell you fx, y, z, what should be the angular part? You can just write down fx, y, z, you know, sin theta cos p times sin theta sin p times cos theta. So that will be the x, y, z. Fx, y, z will have that theta phi dependence. And what is interesting is that you can plot z squared. So z squared is going to be positive in both plus and minus z axis, right? So that's the reason why it is like this. But then there's also a minus this thing minus 1/3 r squared. So that is the reason why for small values of z, you'll have a small ring of negative values here. So this will be plus, and there will be a minus. So you can actually figure out the orbital signs where the orbital is positive and where the orbital is negative just by looking at. So this way, a spherical there are some more that one should worry about, because you will have okay, because all these have a cumulative power of 2. Okay, so that's why they are the second degree cubic harmonics. But you see that are only 5, because you only have 5 d orbitals, right? What are those? They are 5, 2, 2, y2, 1, y2, 0, y2 minus 1, y2 minus 2. So these are the 5 spherical harmonics that you will have. Okay, and the reason why you have only 5 spherical harmonics is spherical harmonics are linearly independent. Okay, whereas here there's a condition that specifies all these things for a unit sphere. For a unit sphere, on a unit sphere, what happens is that plus z squared. So this condition reduces the 5 independent variables that you have, 6 variables that you have into 5 independent variables. And that's why you only have 5 d orbitals, which are cubic. Okay, you don't have 6 corresponding to x squared, y squared, z squared, xy, yz, and zx. Okay. Okay, so I have probably given you a sufficient introduction to the algebra of differential equations. That should stand by you in most of the applications that you are going to do. And in the next lecture, I will talk a little bit about how you can differential equations, because it's very important that most of the differential equations that you may write down may not have analytic solutions. And when they don't have analytic solutions, you still want to have a solution. And the way you can get the solution is mainly by computational techniques or the numerical techniques. And I'll discuss how one can get numerical solutions of differential equations. So I will stop at this point, and any but what you can do is go back, read it, and yeah, you can go back, read it. Yeah, all these podcasts. Mathematics. Okay. So I will stop at this point, and so I will stop here, and we'll meet again next week. Thank you.
Thank you, sir. Thank you, sir.
Okay, bye.